Okay, so welcome everybody to this week's Majorana-Raychaudhuri seminar series. Our first speaker is Utkarsh Kumar from University Ottawa, and he's going to talk about probe of spatial geometry from scalar-induced gravitation waves. And I will send you a reminder when 5 minutes are left.
Yeah. Okay. Thank you. So hello everyone. Today I'll talk about the probe of spatial geometry using the scalar-induced gravitational waves. Yeah. So let's begin. This is a brief outline of my talk. I'll start by discussing about the geometry of the universe, how we measure it in cosmology, and why is it important to measure the shape of the universe. I'll also give some current constraints on the curvature from different measures, and then we will briefly give an overview of the recent measurements of the stochastic gravitational wave backgrounds and the scalar-induced gravitational waves. Finally, we will discuss that how can we include the effect of the spatial curvature in the scalar-induced gravitational waves settings. And finally, I will talk about the how the spatial curvature impacts on the pyramidal black hole formation. Right. So the first question that one can ask is that the what is the geometry of the universe? So in principle, one can have three type of the geometry, namely open, flat, and closed universe. So the geometry of the universe comes into picture using the FLRW background. So in the FLRW background, K parameter encodes the geometry of the universe. Depending on the values of K, it can be either open, closed, or flat universe. The geometry of the universe can also be quantified by writing the first FRW equations such that the contribution of the curvature is written as in terms of the energy density called curvature density, which is scales as a raised to power minus 2, and the coefficient of the curvature energy density is parameterized as following. So we note that the signature of the k or and omega k are opposite. For example, if we have k is minus 1, then omega k will be positive and the universe will be open. So now I'll discuss why it is important to determine the spatial geometry of the universe. So it can be important for at least two different reasons among the others. So from the late universe perspective, the sign and the value of the curvature density plays an important role to determine the fate of the universe. So for example, if we find that the omega curvature density to be negative, which will mean that universe is closed, and due to this negative curvature density, universe will be in distant future will be collapse. So this might pose a problem in cosmology. Now, from the early universe perspective, measuring spatial curvature is quite important because as we know that the inflation is the success of inflation depends on its capability to probe to explain the flatness problem. So now all the inflationary models are built to provide the omega k to be 0. Now if we can measure omega k to be order of 10 to power minus 4 or larger than that, then the most of the inflationary model will fail. So these two reasons there is at most important for the measure, like we should be able to measure spatial geometry from the different measurements at different scales. So now I'll present the recent constraints that we have on the curvature density from the different measurements. So the first constraint comes from the Planck measurement. So as we see from the contours on the left here, from the Planck measurements, there is an evidence of the closed universe at 99% confidence level. If we take this result at its face value, then we find that universe is a closed universe, and it will collapse at some at in the future. But now we also look at that other values of the values of the Hubble parameter and omega meter, they are a bit skewed, and this and the explanation of the as compared to their lambda CDM counterparts. So now the answer comes from the geometrical degeneracy. So now if due to the geometrical degeneracy, people in the community do not consider the measurements on the omega k from the Planck 2018 data reliable. So, so in order to make this constraint on the omega k reliable, people often um, combine Planck 2018 data to the Bow data. So in the right contour, we present the constraint from the combining Planck plus Bow, and we find that the universe is again consistent with the our standard understanding that it is flat universe. So now basically I'm presenting only two measurements, but there are several other measurements that are also have in tension with Planck, that the Planck gives the closed universe, but if we combine Planck data plus other data, it will always give the flat universe. So we should so now in our talk we are focusing on the gravitational waves because they offer us to probe small scale physics. So the recently nanograv and along with other collaborations such as IPTA and EPTA have predicted a stochastic gravitational wave background. However, the origin of the signal is not yet clear. It can be astrophysical or primordial. If origin of the signal is astrophysical, then no, is origin of the signal is cosmology, then one can use this signal to probe the new physics of early universe. For example, the observed signal from the nanograph EPT and IPTA integrated have been interpreted as a cosmic strings, domain walls, primordial gravitational waves, and the second order gravitational waves induced from the first order curvature perturbations. There are future missions like LISA and DESIGO, which corresponds to the small scales and will provide the measurements at scales ranging from the nanohertz to millihertz. So now we will briefly review the what are the scalar induced gravitational waves. So as we know that the at CMB scales, primordial gravitational waves are much weaker compared to the scalar perturbations. The constraint on the scalar to tensor ratio is always greater is bound by the following number. On the other hand, scalar perturbations compared to the tensors have been studied very well on a very wide range of scales varying from the CMB to LIGO scales. It has been shown that in the several inflationary models that there can be an enhancement of the scalar perturbations at the scales relevant to the PTA and the other future gravitational waves background. So now, if we go beyond the first order in the perturbation theory, then one finds that at second order or higher order, um, the scalar vector and the tensor perturbations interact with each other and act as a source for the higher order perturbations. If we assume if we assume that the curvature perturbations are enhanced enough, then the higher order second order gravitational waves will be first order first order scalar perturbation will act as a source for the second order gravitational waves, and which will dominate if we give enhance if the first order perturbations are enhanced enough. So this is called the scalar induced gravitational waves. Traditionally, scalar induced gravitational waves have been studied for the k equals to 0 case. So, but now in this work, we will try to generalize this paradigm, and so now we will try to derive the equations for the scalar induced gravitational waves in the non-flat universe. So we will start by describing the FRW background perturbed of the second order. So in this background, phi is capital phi is the Newton is a scalar is a scalar perturbation, and in Hij is a tensor perturbations. At the zeroth order, one can write down the Einstein equation, first and second Friedman equations as follows. So here we can see that rho and P are the energy density and the pressure of the fluid dominated during the reheating era. Uh, Now the background is fully determined if we can by solving the Einstein equations, such that we can find that the scale factor in terms of the conformal time for the different geometries. Now we will describe now we will describe the first order scalar and tensor perturbations in the general FRW background. So at the first order, scalar perturbations can be decomposed in can be can be written in time, space-time, and space components. And now it is straightforward to combine these per- these three perturbations to give the to give an evolution equation for the scalar perturbations at first order. Similarly, same practice can be done for the scale for tensor perturbation to give the similar kind of equation for the tensor perturbations. Since the tensor perturbations are the gauge invariant and the traceless and transverse quantity, so one might need also the a projection operator in order to in order to check the traceless and transverse nature. And this projector operator is given as follows. So now we are ready to write down the evolution equation for the second order, which are second order tensor perturbations, which induced by the first order perturbations. So the second order evolution equation for the second order tensor perturbations looks like pretty much same at the at the left hand side as a first order, but there is a extra additional source that is coming from the first order uh, f- uh, coming from the first order perturbations. This source can come in three form. First is the scalar form, second is the scalar tensor, and the third is tensor form. As we notice that there is no vector form, a vector perturbation sourced here, because we know that the vector perturbations are known to be decayed, and that's why we don't see that's why they are always subdominant, and that's why we don't see any effect here. Also, on the top of that, as I mentioned earlier also, that tensor perturbations are weaker than the scalar perturbations. So the scalar tensor and tensor term also will be always some subdominant compared to the scalar ones. So in principle, we only study the scalar term and omit the scalar tensor and tensor term. For the generality, we give all the contributions for the all the sources here, but we only consider the scalar term for our investigation. Yeah. So now the all the equations presented in previous slides are written in the real space. In order to study like cosmological quantities, the key quantity is the power spectrum of the perturbations. For this, for the studying the for the calculation of the power spectrum, it is convenient to transform the equations from the real space to the Fourier space. So in flat case, it is often used to do so. To go from the real space to Fourier space, one often use the Fourier transform, because we know that in the flat space Laplacian admits of plane wave solutions, which follows the simple eigenvalue problem, simple this eigenvalue problem. But things are a bit tricky in the non-flat case, as the eigenfunctions of the Laplacian are cannot be expanded in the as a plane wave solutions, as exponential plane wave solutions. But now here they are expanded in the scalar and tensor harmonics. So so for the tensor harmonics, there is a eigenvalue is n square minus 3k, while the scalar or harmonics, the eigenvalue becomes n square minus n square minus k. So this so we as we see that the role of the spatial geometry comes in the picture in at the Fourier modes at even at the Fourier modes level. So now we have to expand tensor and the scalar perturbations using their corresponding scalar and the tensor harmonics as following. Now substituting these expansions into the evolution equation here, uh, we find we find that the evolution equation for the tensor perturbations for each mode in the wave, wave numbers as following. So now we will try to give up a form of the source term in the Fourier mode representation. So we can use the scalar harmonics. So scalar harmonic expansion for the source term to express as following. So now so as we as we note here that there is a summation over all the quantum numbers n, l, and m. Furthermore, since source has to be traceless and transverse as it is source to the gravitational waves, so we have to operate. So we have to extract the only the traceless and transverse quantities from this source. So we have to we operate that the projection operator over this source, and we get the following result. And finally, we also use the correlation property of the harmonics given as following. So this property can be extracted from the can be extracted from the relation from the definition of the harmonics to give the final form of the source is as following. So now we are in position. So now we can find the evolution of the tensor modes and start calculating the 2-point correlators and extract the power spectrum, the gravitational waves. So the evolution of the second order tensor perturbations is given as following. So we employ the Green's function method to find the solution of the this source differential equation in homogeneous differential equation. So the general solution is given as following. It's a product of the source term and the Green's function. Since we are interested in the modes which re-enter in the horizon, mm, and so hence we can decompose the first order scalar perturbation into its primordial value zeta NLM and a transfer and a sub-horizon transfer function TNLM. So inserting this quantity into general solution, one gets more um, one gets one gets the following the tensor perturbation becomes following where I NLM is this quantity is called the kernel. So this kernel is derived from the source term and plays an important role in the evolution of the gravitational waves. In other words, it acts as a transfer function for the gravitational waves, which connects the super horizon gravitational wave spectrum to the sub horizon gravitational wave spectrum at the radiation era. So now we can finally extract the power spectrum by for that we calculate the 2-point correlators, which is defined as following, and 2-point correlators are connected to the power spectrum in this following way. So now we can extract the power spectrum by from these equations, and after the tedious calculations, one can write down the power spectrum for the gravitational waves as following. So in this expression, we see that there are terms proportional to the gamma n. So these gamma n terms are the corrections coming from the inclusion of the spatial geometry. So now if we take the gamma n to be 0, it reproduces the flat case. So flat case result. So we note that the account, like including the spatial curvature, even modifies the expression of the power spectrum. So now finally we can relate this tensor power spectrum to the gravitational waves in this via this relation to in order to estimate the gravitational wave spectrum at the reheating. So now the final task is to evaluate kernel. So kernel is usually defined as an integral of the multiplication of the source term f mean uess and the Green's function. So the Green's so here Green's function and the fss are following in the following way. Sorry. Yeah, this. So now, so firstly we will derive the expression for the Green's function and the scalar transfer functions. Green's functions and the scalar transfer functions can be derived using by solving the first order scalar perturbations that given in previous slides. We solve them. We solve the first order perturbation equations in the subhorizon limit in order to give the following form of the Green's function, the tensor transfer function. So again here we note that that the quantities beta n and beta u encodes the corrections due to the spatial curvature given as follows. So now using all the expressions for the Green's function and the tensor transfer function, one can find out the one can rewrite the kernel equation in the following form. In the this is again a very cumbersome form, but and we have omitted all the calculation mm, process like steps involved in this. And so in this expression there are two terms like this ij ij1 and iy1, which are they are the functions involving the associated legendary functions, and they are analytical. uh, they can be found using the they are the they are available. We know their form. So now basically now we can given the expression of the kernel and the power spectrum, now we if we specify the power spectrum of the scalar perturbations, then we can find the gravitational wave spectrum. So for our purposes, since we are interested in showing the features of the results of the spectrum due to the spatial geometry, so we choose a Dirac delta spectrum of the curvature perturbation. So this type of spectrum is predicted by many inflationary models, and also the choice of the spectrum, this is also is important because it allows you to want to write down the analytical equations for the gravitational waves. Otherwise, we have to rely on the numerical methods in order to um, integrate integrate the double integrals involved in the power spectrum. So the analytical form of the scalar of the gravitational wave spectrum is given as following. However, it is analytical result but does not give much information. So first we will plot some results and show that the how does it depends on the different spatial geometry and other physics. So in this slide, I present the gravitational wave spectrum induced from the pyramidal gravitational waves in modes for the different spatial geometry. So in this plot, k equals to 0 is represented by the solid, k equals to plus 1 is represented by the dotted, and the k equals to minus 1 is represented by the dashed lines for Dirac delta spectrum. So in each panel we present two reheating temperature. One is that this purple color presents the reheating temperature corresponding to 10 GeV, and the red color presents the rating temperature 10 to the power 5 GeV. And we note and we see that that as the rating as the for the low rating temperatures, we can there is a clear there's a clear difference in each spatial uh, in the each spatial geometry of the universe, as we can identify the there's a clear evidence, there's a clear a difference from the flat universe. And while this difference dies as we increase our temperature to the higher values. And another important fact due to the inclusion of the due to the inclusion of the spatial geometry is the appearance of this peak that we see that we see here, which was absent in the k equals to 0 case. So now we will discuss what are the features that we saw in previous slides, and we will try to write down the try to write down the try to get the same features from the analytical results. So as we saw that the gravitational wave spectrum has two peaks, and these two peaks comes from the parametric resonance at happening at the s equals to plus or minus 1. So this peak so the first peak that we see here, at this peak, it happens due to the s equals to minus 1, and this is peaks given as in the following form. While at the second peak, it is solely due to the inclusion of the curvature. At if suppose if we take k equals to 0, then there is this second peak disappears, and this second peak comes from the s equals to plus 1. So now the behavior of the infrared tail of the spectrum becomes important for the non-vanishing k. So we can give now here for the low frequency regime, we can write down the more we can write down the analytical results. We can approximate the spectrum in more in a more practical way. So so there interestingly enough, there exist several limits in which this scalar-induced gravitational waves in curved space background has a distinctive behavior. As the first regime, when the frequency of the when the frequency of the spectrum is much higher, is much larger than the corrections coming from the curvature, and then the scalar perturbation, then the gradation wave spectrum behaves in this way. And when the frequency becomes comparable to the corrections from the this kc square by this, then it behaves in a different way. So as we see here that that due to the inclusion of the spatial geometry, the reheating temperature also becomes important, as we show in the picture that that for the low reheating temperature, one can easily distinguish between the each spatial geometry, and also both and also amplitude and slope of the spectrum are also modified due to the inclusion of k. So now, so far we have studied the gravitational wave signature in the presence of the non-zero k of a peaked primordial spectrum. So now we will now we will discuss about the primordial black hole formation. So the amplitude of the gravitational wave spectrum density measured today will be determined by the amplitude of the spectrum. If peak of the spectrum a zeta is large enough, then the density fluctuations in the very early universe will collapse and can generate the primordial black holes. So the mass of the primordial black holes is related to the frequency of the gravitational waves via this relation. And now the candidacy of the primordial black holes can be tested by estimating the fraction of the primordial black hole to the dark matter is given as following relation. The PBH fraction of the formation which is evaluated using the press sector formalism, can be approximated in this by the following relation. So where delta c and sigma delta are the quantity that we mentioned, the delta c is given by the following expression, while the sigma delta is the power spectrum dependent quantity and can be computed via this relation to get And for the Dirac delta power spectrum, sigma takes this following form due to the and again this term is coming from the non-zero k here. So now we to constrain the parameters for the gravitational wave spectrum, we use the fact that the PBH density cannot exceed than the dark matter. That is, the FPBH is greater than 1. So when FPBH is 1, then the most of the dark matter is in the universe is accumulated by the existence of the PBH. So in the left panel, the region of we show the region of the parameter space for the A zeta and the for the different as a for the different mass of the black holes in grams, such that the pyramidal black hole comprise the totality of the dark matter. And we see that the like almost for the negative for the negative k, there exists like we can accommodate higher mass black holes with such that we do not overproduce the gravitational wave background. And then the second in the right panel, we show that the relation between the mass of the black holes, such that the given for the given spectrum, that is 10 to the power minus 2, we show that the what should be the what can be the constraint on the curvature is in the following way. So finally, I conclude. So we included, so we derived the power spectrum for the scale-induced gravitational waves in the universe filled with in universe with a special curvature. We also observe a significant enhancement in amplitude of gravitational waves with a special curvature when when a special curvature assumes its value to be negative, and for the radiating temperature to be 10 to the power minus 3 to 10 to the power 3 to 50 GeV, 10 to the power minus 3 to GeV to 20 to the power 250 GeV. Due to the non-vanishing special curvature, the resulting gravitational wave spectrum has additional peaks, which can be probed, which is the unique feature of the this KSIGWs, and can be proved from the different measurements. The main features of the this scale-induced gravitational waves are observable for the wide range of frequencies varying from the PTA to LISA, and for the different reheating mechanism, so that we can probe the high and low reheating temperatures. We also derived a constraint on the pyramidal black hole abundance. The presence of the special curvature significantly improves the volume of the parameter space that is available for the pyramidal black hole formations as a viable dark matter candidate. Thank you.
Hello,